Hello friends, so today we are going to discuss two questions, and these two questions are from rotational motion. So the first question, it states that two drums are mounted on same horizontal axis and can rotate freely without friction. The inner drum has a mass ma and radius a. It is initially rotating with the angular speed omega a naught. The outer drum has a mass mb and radius b, where b is greater than a. It is initially at rest but free to rotate. A thin layer of sand with a total mass ms is spread uniformly on the inner surface of the smaller drum. At time t is equal to 0, small holes in the inner drum are opened. The sand starts to fly out continuously at a constant rate of dm by dt, which is given as lambda, and immediately sticks to the outer drum. Assume that the sand takes negligible time to move from the inner to the outer drum. Ignore the transit time. There is no external torque acting on the system. Find the angular velocity of two drums WAT and WBT as a function of time. So here we are going to find out the final angular, you can say, velocity of the drums A and B. Okay. So we can just draw an approximate figure. So we are given a two drums concentric. So let this be inner drum, which is our drum A, and its radius is given as small a, and we are having a outer drum which is given as drum B, and its radius said to be given as b. B is greater than a. Okay. And initially it is said that drum A is rotating with the angular speed of omega a naught. Okay. And there is a sand which is placed inside the drum A. And there are certain holes on this drum A, and when these holes are opened, the sand is going to fly from drum A toward the drum B, something like this. Okay. It will be flying tangentially. Okay, so I think approximately this will work. And it is said that it is going to stick to the drum B. So this is the basic, you can say, question about the. And initially drum B was at rest and only drum A was rotating. Okay, so this is the question given to us. So we can say that we are given that we have an inner drum A its radius is given as small a, and its initial angular speed which is given as WA naught, and let us suppose for the sake of convenience we denote it as WA naught. Okay. And then we have our outer drum, and this outer drum is our B. Its radius is given as b, okay, and initially it is rest. So you can see its initial angular speed. So initially it rests, so we can say that W B naught is equal to 0. So these two are the velocities of their initial velocity rather. And then we are having the sand. So we are given that initial mass of the sand is given as ms. Initial mass of sand, and that is on A, it is given as ms. Okay. And this sand leaves A at a rate, and that rate is given as dm by, second to a smaller peak, dm by dt, and it is given as lambda. Okay. So it means that after time t, the mass of sand moved from A to B, and let us suppose we call this as MBT, and that is equal to lambda multiplied by T. And with respect to this, you can say the moments, which is including the sand with respect to A as well as B. So from here we can say that our moments including sand on each drum so for our A, we can write this as IA of T, IA of T will be equal to the original mass of our A plus mass of the sand, that is original mass of the sand, minus the sand which has moved from A. And similarly, we can write for B, initially and it is multiplied by our A square. And initially we were having our mass of B rim plus the sand in time t, and this is multiplied by its radius, that is a B square. So this is the moment of inertia of with respect to their respective, inclusive the sand. Okay, because our this drum A, so this is with respect to drum A, and this is with respect to our drum B. So here drum A loses lambda times t and drum B gains lambda t. And so we are only looking, we are going to consider a small mass dm, and which detaches from the inner, that is from drum A, and sticks to drum B. Okay, we are going to calculate for this small mass dm, and based on the calculate all the things based on that. So we consider a small instant in which a tiny mass dm of sand detaches from drum A. Okay. So at this particular moment, you can say at this instant, the total moment of inertia of drum A plus remaining sand in our A, and similarly we can find out for our this A as well as B. Okay, so let us, so at this particular instant we can write that the total moment of inertia of drum A plus remaining sand, and this we already has denoted as IA of t. Secondly, you can say that when this small mass dm moves, the moment of this inertia of IA we can just calculate. So we can say when dm dm leaves A, the moment of inertia becomes, so its initial moment of inertia was IA of t, and the new moment of inertia will be equal to our I of t minus the mass which moved and its radius square. And because of this, there will be also change in the slight change in the angular speed. So we can say that the angular speed could change slightly, and from WA to WA plus DWA. Okay. And we are going to make analysis of this, whether this is going to change or not. Okay. And next we come to our angular momentum, because we are basically going to use the conservation part. So this was just the initial discussion. So we come to our angular momentum before and after. Angular momentum before and after. So let us consider before first. And before, let us call this as L before, will be equal to, its was IA of t multiplied by omega A. Later on we can substitute omega A as omega naught and whatever the initial angular velocity was. Now we come to our after. Now in this case, there will be, you can say, let us call this as L after, and we just wrote that after it is angular momentum inertia is given as IA of t minus dm times a square and multiply by omega a plus d omega a. And let's find out the change in angular momentum of A. Change in angular momentum of A, and let us, this change in angular momentum of A is our delta LA. So we can write that our delta LA is equal to angular momentum after minus angular momentum before. Okay, and we simply substitute. So after was our IA of t minus dm a square, and we have this as omega a plus d omega a minus IA of t, and this is our times omega a. And because now if we open the bracket, there will be terms that will be coming in multiplication, that will be dm multiplied by d omega, which we can just ignore because it is very the product will be resulting in a very small value. Therefore we can say that our change in angular momentum will be equal to our IA dwa minus dm a square wa. And in this case we have to remember that the product of dm and dwa is ignored. And okay, now let's find out, we can say apply the angular moment conservation. Angular momentum conservation, and it is given that there is, in the question itself mentioned, that is there is no external forces or external torque is there. Therefore we can say that our angular momentum will be conserved. Our total angular momentum, that is drum plus sand, is going to be conserved. And so if we substitute it, we can say that our delta LA plus angular momentum carried away because of the sand movement will be equal to 0. Okay. So it means we already know that the angular momentum that is being carried away is our dma square omega, and therefore we can say that our we can write that because the momentum will be taken away by the sand, so we can say the sand that left carries away, and that momentum is our dm a square times omega a. So it means that for total angular momentum to be conserved, so we can say for total angular momentum to be conserved, the delta L, because we have written here this change in angular momentum plus angular momentum taken away should be equal to 0. Therefore, from here we can say that our change in angular momentum should be equal to minus of dm and a square omega a. And from here we can also say that our IA times dWA should be equal to 0, because from here this is equal to 0. Therefore, we can say that IA times dWA should be equal to 0. Okay. So which basically means that dWA should be equal to 0. And thus from here we can say that a drum's angular velocity does not change. Okay, because this is dWA, the change in is equal to 0. So from here we can say this WA is our constant. If WA is constant, therefore we can draw a conclusion that the drum's angular velocity does not change. Okay, so if the angular velocity is not going to change, and we are given in the question that its initial angular velocity, we are given that its initial angular velocity, which was our WA 0, and we have assumed it as WA naught. Okay, so if it is not going to change, then this WA naught should be equal to our WAT, which is our angular velocity at a certain time t. Or in the simpler terms, we can write that our WAT is equal to WA naught, and that will be constant for all time t during the transfer. Okay, so we can say constant for all t during transfer. And also, if you look physically, you can say physically also, because there will be, we can say that our, even if the little bit of sand leaves, the angular momentum is going to remain same, because the moment of inertia as well as the angular momentum are dependent upon the, you can say, the mass which is being left. So there is a adjustment in both angular moment, the moment of inertia as well as the angular momentum. So both are going to change with respect to the same value. Okay, if both are going to change with respect to the same value, then the, you can say, product of I omega is not going to change. Okay. This was entire discussion was our with respect to let me write it here, drum A. Now we come to our drum B. So you can say at drum B, and we already know that at any time t, the moment of inertia of B, we have already written the equation that IB of t is equal to mass of B plus lambda times t and multiply by B square. Okay, and we have taken that its angular velocity is our WBT at a certain mt. Initially it was equal to 0. And here also we are going to use, because from A small mass dm is coming out, and that small mass dm is going to stick to our drum B. Therefore we can say that small mass element small mass dm, which is equal to lambda times dt, is leaving A and arrives at B. And we already know that the angular momentum that is being carried by this small mass m is dm a square omega at. Okay? So we know that sand particle carries angular momentum, and that angular momentum is our dm a square and omega a, and that is dependent upon time t. And we already know that our omega a is omega a of t is equal to omega a naught. And it is given in the question that this sand particle is going to stick to our to the drum B. So basically there is inelastic collision, and the transit time between A and B is said to be ignored. So let us once again discuss the before and after in case of our this B. So we can say our angular momentum just before contact and let us call this as L before, and we can say that our L before will be equal to IBT omega bt plus dm a square, and we have this as omega a naught. Okay, because we know that our omega t is equal to omega a naught, okay, which is not going to change. And let's find out after it sticks. So we can say angular momentum after sand sticks, and we can say this as, let us find out, this is, let us call this as L after, and for this we are going to calculate the new moment of inertia. Okay. So we can say the new moment of inertia, which is our IB, and T plus dt will be equal to IBT plus dm times b square. Now we can just write our angular momentum after, that will be equal to our IBT plus dm b square times omega b plus d omega b. And we can use now angular momentum conservation. Angular momentum conservation, and this angular momentum conservation, it is going to give us our angular momentum after is equal to angular momentum before, and we simply substitute both the equations. We get this IB of T plus dm b square times WB plus d omega b is equal to IB omega b plus dm a square and omega a naught. Okay, now we are going to solve over this left side, and we can just open the bracket. It is going to sort out everything. Therefore we can write that our omega b, yes, here it is b, not a. So we open the bracket, we get this as our IB omega b plus IB d omega b plus, and we get this as dm b square omega b plus dm b square and d omega b, and this is equal to IB omega b plus dm a square times omega a naught. And in this case we can just ignore this term, and IB omega b, they cancel out with each other. Therefore we get that our IB d omega b plus dm b square omega b is equal to dm a square omega a naught. And now we can just rearrange it, because it will be some sort of differential equation, and we divide both side by dt. Okay, and we also combine our like terms. Okay, now let's first divide it, then we can solve it further. So we get this as our d ib d omega b by dt plus b square omega b dm by dt is equal to, and we have this as our a square omega a naught and dm by dt. And we already know that this term dm by dt is nothing but our lambda. So we can move that on the right side. So we get this as our ib d omega b by dt is equal to, and we can take lambda is common. We get this as our a square omega a naught minus b square, and this is omega b. And we already know the value of our ib, therefore we substitute that our ib is equal to our b square and times mb plus lambda t, and this is our d omega b by dt is equal to, this is lambda a square omega a naught minus b square, and we have omega b. And we divide throughout by b, and along with that we also divide by this complete term. Okay, we are going to form it as a differential equation, and we get that our d omega b by dt, and on the left side we are going to bring this omega b on the right side. So we get this as our plus, and we have divided by b square. Okay, let me write it first. B square, and this comes as b square mb plus lambda t, and this comes as times omega b is equal to, and lambda a square omega a naught b square mb plus lambda times t. And here this b square cancels out, so we get this as d of omega b t plus, here lambda is missing, and this will be plus lambda times mb plus lambda t omega b is equal to, on the left side, on the right side it will be entirely the same terms, lambda a square omega a naught b square minus of b lambda times t. And this is our, you can say, differential equation for omega b, and that is going to govern how the angular speed of the outer rim, that is b, is going to change. Okay. So let us use the initial condition and solve this particular equation. So we know that especially our omega b at time t is equal to 0 is given as 0. Okay, that is already known to us, and we integrate it from 0 to t. And okay, so we can write this as integration dwt upon dt plus integration lambda upon mass of B lambda of T multiplied by omega B is equal to integration, and we have this as lambda A square omega A naught B square m of B and lambda of T, and we are going to integrate from 0 to T. So our and okay, so this gives us mb of T times lambda T and multiply by wb of T and minus, and this will be our mb plus 0 and multiply by omega b of 0, which will be equal to, and we get this as lambda A square omega A naught, lambda A square omega A naught divided by B square, that will be constant, and that will be multiplied by our T. And we know that this omega B is equal to 0, therefore we can write that mass of B times lambda T multiplied by omega B of T is equal to lambda A square omega A naught B square times T. And from here we can just write our omega of B of T, which we are supposed to find out, and this will be coming as lambda A square omega A naught B square, and we have this as mb of times lambda T, and this T we can combine here with lambda T, because we can just, because we know that our lambda T is nothing but mb of T, so we get this as our A square omega A naught and B square mb, and we can write this as small mb of T, and this is also equal to mb of T. So this is our velocity of our B, which we are supposed to find out. And I think this was the thing which was asked for. We already got WAT, we already got WAT will be equal to initial, and this is our WBT. In this case we can, in the question it was not asked for, but still we can find out with respect to, you can say, what happens to the rotational kinetic energy as the sand transfers from A to B. So let us make a with respect to the kinetic energy. So rotational kinetic energy, and we already know all the formulas, so let us straightforward go into the kinetic energy part, and we can write that at any given moment time t, the total kinetic energy of the system will be the kinetic energy of drum A plus kinetic energy of drum B. Okay, that is a total rotational kinetic energy. You can say at any time t, total rotational kinetic energy, and let us suppose we call this as k of t, and this k of t will be equal to energy associated with our drum A plus energy associated with our drum B, and we are only talking about the rotational kinetic energy. Okay. And we already know our I of A we know, and I of B also we know. So we substitute them, we get k of t is equal to, where this is half, and we have our IA square, mass of A, mass of sand minus lambda of t, and this is our omega A naught square plus half B square, mass of B plus lambda of t, and we have this is omega B square. And we already know that our omega B is equal to, this is our A square omega A naught upon B square, and this comes as a lambda of t times mass of B plus lambda t. So we substitute it, and so we have to solve this part. So let us deal with separately. So we can say that our B square mb plus lambda t, and we have this as lambda B square, and therefore we get this as A times 4 omega A naught square times, and this is our B times 4 multiplied by lambda square t square, and we have this as mb plus lambda t whole square. And okay, so we can just, this goes by square, square goes by this 2, so we are left with that this term will be equal to our A4 omega naught square and B square lambda square t square m of B plus lambda t. Now we can substitute our total kinetic energy. So we can say that our k of t will be equal to our half A square omega A naught square mass of A plus mass of sand minus the mass moved plus half, and we have this as A of 4 omega naught square B square times lambda square t square mb plus lambda t. And we can make a comparison between the initial kinetic energy and the final kinetic energy also. So we can say our initial kinetic energy initial kinetic energy means that at T is equal to 0, and we can write that K of 0, and we simply substitute 0, so this term goes away and entire this term vanishes. Okay, so we are left with only our half a square omega naught square m of a and mass of the sand. Okay, so it means at only T is equal to 0, because only inner drum and the sand is rotating, outer drum is stationary. And at a certain time, you can say that is final kinetic energy, and we can assume that at certain time T is equal to capital T. All the sand has moved from A to B. Okay, so we consider this time as all sand is moved from A to B. Therefore, we can write that K of T is equal to our half a square, and we have this as omega naught square, and there is no sand on A, so there will be only the multiplication of, because of our mass of the wheel drum A, plus entire mass is shifted to now block B, drum B, so that will be plus half, and this comes as our A4 omega naught square B square, and we have this as ms square, and this will be mb plus ms, because this delta T is nothing but our small mass m. Therefore, if entire sand has shifted from A to B, then this delta T will be equal to our mass of the sand. And if you find out the change in kinetic energy, that is our delta K is equal to kinetic energy at T minus kinetic energy at 0, and we have our this term will be present in both, so we can just take it common, and we have this as half a square omega naught square and multiply by mass of A plus, and then it comes as A square by B square, and the second term A square by B square, and we have this as our mass of sand square plus mass of B plus mass of sand minus, and that is equal to only MA plus MS. And if we solve this, we can take this as LCM, so we are going to get this as our there is no need to take LCM, you can just sort it out here, because this MA and MA is going to cancel out, and we are going to get this minus of MS and keep rest of thing as it is. So we get this as our half A square omega naught square minus mass of sand plus A square upon B square mass of sand square, and we have this as M of B plus M of S. But we are given that B is greater than A. Okay, so we know that B is greater than our A. Therefore, the second term will be much less than the first term. So from here we can say that our delta K will be less than 0. Okay. Or we can say that total kinetic energy is going to decrease during the process. Okay. So this is a little bit of discussion about the kinetic energy also. Now we come to our second question. It states that a hollow cone of height h and base radius r can rotate freely about a fixed axis, vertical axis. A narrow frictionless groove is cut along its surface from the apex to the base. The cone is initially set into rotation with the angular speed omega naught. A small block of mass m, small m, is released from rest from the apex, that is top, and slides down the groove under gravity. The block always remains in the groove, it does not leave the surface. The moment of inertia of the cone about its axis is given as I naught. Find the angular speed of the cone when the block reaches the bottom of the cone, and find the speed of the block in the initial frame when it reaches the bottom. Okay, so we have to find out the angular speed of the cone and as well as angular speed of the block. So we can just draw an approximate figure for the given question, and it is given that we have a cone. So let us draw a cone, and this cone is having a slot. Okay, so let us draw the slot somewhere here. Okay, and in this slot, this